Okay, moving on. Problem 3. I sort of printed the worksheet out into a PNG file or PDF file and turned it to PNG file and tried to get the diagrams the right size. May not have completely succeeded, but whatever. So for part A, that's here, we want to find the flux through this face of this cube. We have this positive charge in the middle, and we know the cube is centered on the origin where the charge is. So this cube is centered on the intersection of these axes, and the cube has a side length of d, and everything's arranged all nice and neat. Okay, so we want to find the flux through the shaded face only. Now the flux of the entire cube is given by Gauss's law, which just says that the total flux out of a closed surface, the total electric flux out of a closed surface, is just equal to the enclosed charge divided by epsilon naught. Okay, and in this case, the entire cube, the charge, so I'm going to say phi with the subscript c is the electric flux out of the cube, is just that charge q divided by epsilon naught. So this is the total flux coming out of the entire cube. Okay, whole cube. Now, how much comes out of just this one side? Well, this isn't too hard. If you think about it, the flux going out of each of the 6 sides has to add up to the flux out of the whole cube, right? All the flux out of the cube has to go out of one of the sides. And if you think about it a little bit, there's some symmetry here. You can turn this cube in a direction. We could be looking at the top face, and the same logic would apply because everything's nice and symmetric about the axes, and this thing in the middle. You can realize that the flux through all 6 sides must be the same. So in fact, the flux through one side, or really, if we want to say the flux through all 6 sides must be the same, so if phi sub s is the flux through one side, 6 times phi sub s has to equal the flux out of the entire cube. Okay, so you take all the sides, add them up, and they're all the same, then they equal the cube. This is the longest solution to a short problem ever, but what this means is that phi out of that one side, flux out of one side, is just this divided by 6, and so it's going to be that charge divided by 6 epsilon naught. Okay, there we go. Now I'll switch to a different one for part B, which is where you have a trickier situation. You have these 2 charges, and the first one is at the origin. This is our same old charge. It's the same cube as before. The second charge is a distance d away from the first one along the x-axis. Now what does this mean? So first of all, it means that if we were to draw like a top-down view, or actually I'll just even do like a front view. So there's our y-axis, and here's our x-axis. We have one charge here, and the other charge is here. Now, this distance here, this is the width of the cube, this is d, right? Which means that if this charge is centered in this cube, and it is, then this distance here must be, now, I don't want to write it in here, but this distance must be d over 2. And since this whole distance here is d, this distance from here to here is d as well. This distance must also be d over 2. So what we have is that this cube is the same distance from this face as this cube, right? I'm sorry, this charge, excuse me, is the same distance from this face as this charge. And if you think about it now, these two guys are basically on opposite sides of this one face of the cube. So here I'm going to draw, here's the shaded face of the cube, okay? Here is the x-axis. Wow, that is the least straight line ever. Okay. Here's the x-axis, okay? And we've got these 2 charges on opposite sides at equal distances. Trust me, these are equal distances. Okay? Now if you look at any point on this face, you're going to have, for example, let's say this point, these are both positive charges, right? So this one's got a charge of plus q, this one's got a charge of plus q. And if you look at, say, this point here, then this guy here is going to have an electric field pointing that way. This guy here is going to have an electric field pointing that way. and they're both going to be the same magnitude, even though I can't draw two arrows the same to save my life. And moreover, their horizontal components are going to cancel. So what I've drawn here in blue is the, sort of each charge's electric field laid over them. And now I'm going to use another color. Let's go with purple. Why not purple? And the net field there goes that way. If you go down here, the net field goes this way. And so you can see that the net field, due to these two, at all points on this, will be parallel to this surface. Because any component of the field that goes into the surface or out of the surface from one of them will be canceled by the field of the other one at that point. So when the electric field is always perpendicular to the surface, that means the flux to the surface is 0. So flux through the side here, this side here, is 0. Now you can't tell what the flux is through the other 5 sides anymore. You don't get that because you have the 2 charges now. You can't say these are all in symmetric situations. They're not. But you can say that this side has a flux of 0. Another way to see this is to draw a second cube. You can draw a second cube with its face adjacent, or one face abutting the first cube, right? And the second cube will have, let me see if I can finish my second cube there. There we go. We'll have this cube at the center, okay? And now these two cubes are identical. They're both side length d, and each one has a charge at the center, and they share this one face. And so then you can say by symmetry, well, if there's flux through this cube going that way, if there were flux going through this face, you should be able to flip the whole problem over and have the same thing be true. And